Hello there. Today we have an Ibanez Sonic Distortion SD9, an original old one. And this pedal has quite an unusual fault in that it actually works fine and sounds great. But if you hit the foot switch to turn it off, there is no clean signal at all. So the effect works, but there is no bypass signal. Let's get right into it. Right off the bat, I noticed some of these solder points look a bit rough. I think there was some retouching done here. So you can definitely tell in the middle here and down towards the bottom, some of those look pretty rough and dry. And we'll keep this in mind. Usually when it comes to like a bypass signal not working properly or anything, you would expect, okay, it's a switching situation, so there might be a broken connection, bad contact in the foot switch, whatever. But keep in mind these old Ibanez pedals are not true bypass. And instead of your regular foot switch, all you got is this tiny little micro switch in here. And the switching itself is entirely solid state. So let's have a look at the schematic maybe. Alright, so here's a schematic I pulled off the internet. No idea if it's correct and perfect, but anyways, shout out to the creators still. Very, very roughly, without going in too deep. The guitar signal comes in here, and this will be the output. The guitar signal does never reach this bottom section here. We can ignore this for now. So the signal flows in here. This is a buffer. And after that, it splits paths and it basically flows at the same time through another buffer and up to a little switch, which it can't pass. So this one will be a clean signal or your clean tone, your bypass. Then if we go back to like the fork in the road here, the other half of the signal goes into this part of an op amp where the distortion effect is created by means of these diodes and some filtering and whatever. And it comes out after your tone and level control to another electronic switch, which it can't pass. If we take a closer look, those have inputs labeled effect off and effect on. And if you would imagine you switched this one on, then of course the distorted signal can go through here, another buffer, and to the output. But if on the other hand side this one was switched on and this one turned off, then the bypass signal could flow through and you would hear like your bypass or clean tone. So how do we control these two switches, or these two solid state switches, because you cannot physically move them with a finger. They need a voltage applied here to switch on. And this is where the bottom schematic here comes into play. So that means in this pedal, 1, 2, 3 transistors do nothing else but switch the thing on and off. In these two here, in this sort of crisscross arrangement, this is called a bistable flip-flop. And this one down here will be your momentarily closed foot switch. It says momentary foot switch. And it's configured in a way where one of those is always turned on, like a switch again, and the other one will be off. And once you briefly close the foot switch, they will flip over and the one which was turned on will now be off and the other one will be on. Whatever. The third one is just powering the little status LED. So it follows one of them. It follows the one labeled effect on. If this one switches on, at the same time you get the red light. Simple as that. So if we see there's an output on the right hand side called effect off. So if this one switches on, we get a signal to effect off, which in turn will switch this one on, and the bypass signal can flow through to the output, and vice versa, of course. So if we get either the distorted signal or none at all, I can say pretty much that this part of the circuit works. And the red LED is working as well, which comes from the effect on side. So my guess is this half will be all right, and this part will be all right. I believe if this transistor was broken, the entire thing wouldn't even flip-flop at all. So just the fact that I can switch it back and forth means, or should mean, that this entire thing is okay. My guess is this part might be faulty. Let's try to find it on the PCB and maybe unsolder it so we can measure what's going on. This is the part number, or not really the part number, but like the what the thing is called. It's a 2SK30A. Let's have a look for this. If we flip over the PCB and have a close inspection, all these black thingies here are transistors. And those two in the middle here are our SK30A whatevers. Now all we need to do is figure out which one is for on and which one is for off. Unfortunately, there's no real helpful labeling on this PCB here for us. And I don't really want to trace it, but there's something else we can do. I got a paddle hooked up to my lab supply, just a dummy plug in there so it turns on. And instead of playing the guitar through it, I'm feeding in like a sine wave from my function generator here. You don't really need it, it's just more convenient than sitting here and strumming a chord all the time. And instead of plugging the output into the amplifier, I am using just a little crocodile, alligator cable, whatever you want to call it, with a little capacitor in front. And I can basically go in and probe signals with that. The capacitor is just to save the front end of my amplifier. So if I find the input pin here, I can hear some signal, and I might turn this up a little bit. I usually ground this thing before I probe, just so I don't accidentally have any DC in there. So let's try. Is this the input? You can hear that it's kind of making bad contact because of all the flux and whatever is on the PCB, but this should be the input. So I can figure out what's going on here just by probing. Okay, check this out. These three pins are one of the electronic switches or field effect transistors, and these three pins are another one of them. So we need to figure out which one of those is for the clean signal and which one is for the distorted signal. This side and this pin will be the output for those, and as you can see, they're joined by a trace. So if the pedal is switched to bypass, we expect bypass signal here, which is not happening. And if we switch it to distortion, like I have it now, we would hear the distortion signal on these pins. So this is just going to be a distorted sine wave. Right? Now let's probe the input pins. On the input side, oh, this sounds remarkably different. Hear that? So this is the distorted sine wave, and this is the clean sine wave. So this tells us this device on the bottom here switches the clean signal, and this we expect is to be distorted, and it is. Just a lot more overtones, whereas this is a pure sine wave. Here's a fun little party trick. Instead of the transistors, I'm temporarily putting in some of these sockets here, so I can switch them in and out and change places and try different types. And now, first thing to do after verifying it still works as before is to switch both of the transistors. So this one is just marked with some tape, and this is the one I assume to be dead. So I can just put it in the place of the other one carefully. Then we can test it again, and we will expect to have clean sound but no effect. And if that's the case, then we know for sure that this transistor is broken. Okay, power it up. Let's drum a guitar. Nothing. And that's the distortion channel. Interesting. So no matter which transistor I put where, the clean side is always not working. This tells me both transistors are okay and the fault is somewhere else. Okay, gotta dig deeper. Back to the schematic. So it's neither this JFET nor this JFET. That leaves us with this circuit itself, which is number and one side. Check this out. We have some clean signal. And we have some overdrive. And clean. I almost don't want to film this. I mean, you wouldn't believe what fixed it in the end. So, remember in the beginning when I told you those solder joints up here looked super sketchy and the traces are kind of burned? Yeah, I should have investigated that right away. But it's not that I didn't. I went in there with like a continuity tester and tested across the traces from one point to the next, and I found out, okay, they all seem to be connected. But just up here, from this point to there, there's the diode connecting the flip-flop to the JFET. So this diode over here. And I was comparing voltages back and forth, and I noticed this side is dropping more voltage than the equivalent diode on the other side here. And I was wondering, hey, what's going on here? And apparently, like dropping an extra volt or something caused the voltage that arrives at these JFETs here to be just not enough to switch. And that was due to bad solder joint. It's always the same. Dang. Yeah, it's just... and I mean, I always keep preaching this and I should follow my own sayings, but yeah, rework all the crusty looking solder joints before you even go into troubleshooting. Like in my experience, 90% the problem is some solder work or some cracked joints or cold joints or whatever. And I was like pulling my hair out and trying to switch parts around and desoldering transistors and switching them over and keeping track of what I do. And yeah, I mean, time to solder the missing parts back in, clean up the joints and put it back together. Then we can plug it into an amp quick and get it back to the owner. So we're all plugged in and it's working. The Ibanez SD9. It sounds just like an SD9. It's a hard clipping op-amp distortion. But the effect worked before. What we're really interested to see is if the bypass works. But before that, here's my drive tone. And now for the glorious bypass signal. Yeah, well, thanks for watching. I hope you still found it interesting, even if the repair turned out to be something very simple, but that's often the case with a repair. The troubleshooting is the interesting part, whereas the repair itself is often just a few solder points. Thanks for watching, and I'm gonna catch you next time. Bye.